All right, so I want to go into another example here of these inclined plane problems. If you have started on the next homework, you have probably seen that these kind of problems are the focus of that homework set. So you can infer that these are pretty important to be able to understand. Not all of them are going to be set up as an inclined plane, but they all solve exactly the same way. It's just about adding vectors. It's all about finding your component vectors and adding them up and understanding Newton's second law. So we'll take a look at this example here. So we have some kind of inclined plane. We have a box and we know the mass of the box. We're going to say the mass of the box is m. And there is some plane here that is inclined at an angle theta relative to the horizontal. And what they're asking us to find here is let's say we start this off in the horizontal and we continue to increase this theta until the box starts to move. So at some point that box is going to move. And what we would like to know is what is the coefficient of friction between the block and the inclined plane. I kind of talked about how to do this a little bit last time. And so this example is just going to walk through that. So the first thing we do is we develop our free body diagram. So we know that at some point, at whatever this angle is, this thing is going to start to move. So we already know a few things. Notice that we've decided that our velocity here is a constant. But that tells us something important. That tells us about the direction of motion. So it kind of tells us how to set up our axes. So our positive x direction in this case is going to be down and to the left. We've set up our weight vector. Now we know that this is going to act along the vector of the acceleration due to gravity. And that's going to be weight. Remember, weight is just a special case of Newton's second law. Instead of F equals ma, we use W equals mg. That gives us something called weight. Remember, we still have to work in kilograms and meters in order for this to work. So don't put weight in as pounds and expect to get something reasonable. So we've got our weight vector. We know that we have a normal force that's going to act perpendicular to the plane of motion. So this is the force that is the ramp pushing on the box at an equal magnitude of the box pushing on the ramp. And then we know we have this F sub small f. Sometimes I just write this as lowercase f. This is our force due to friction. Well, remember, we're asked to find the coefficient of friction, not the force. Now, coefficient of friction does affect the frictional force, but we want to know the coefficient. So our strategy for this problem is going to be to first find what the magnitude of that force is. And then once we know that, we can then find out what the coefficient of friction is. So this is basically a two-step problem. Well, two and some sub-steps. So the first thing let's do is let's draw out our vectors. These diagonal vectors really don't do us a whole lot of good. We need things in terms of nice X and Y. So notice that here is our XY plane that we set up. We chose this to be parallel to this angle. That makes it work out a lot nicer, makes the math easier. Here's our weight that we already know about. Here's our normal force we already know about. And here's our frictional force that we already know about. We're going to add these two purple forces. So this one that acts opposite the normal force. This has to be some percentage of this weight force. So what percentage is it? Now you might look at this initially and think, wait a minute, what the hell? That's a y component as we have it set up. Why is it cosine? We have to go back to our basic geometry and think about similar triangles. Or you could simply draw this piece here as its own right triangle and think about what we know. We know this vector here, W, which is just mg. And we know an angle. In this case, the angle that we're going to look at is going to be here. And it's going to happen to be that theta. It's exactly the same angle. Again, go back and review your basic geometry and basic trigonometry, particularly about similar triangles, and you'll see how we can prove that that theta is equal to that theta. Well, when you do that and you use your trig functions, it works out that this vector here is the cosine of that angle. So remember I told you when I talked to you about angles and using trig functions that in general, your x direction is going to be associated with cosine and your y direction is going to be associated with sine. But I also had a little caveat that said that may not always be the case. Well, here's a time where that's not necessarily the case. And it just has to do with the way we've set up our coordinate system. So be very careful about that when you draw out your free body diagrams. Well, if this vector is the cosine piece, then we still need this part of the triangle. Well, that vector has to be the sine piece. And notice that we don't really care about the scale of this thing. So we're only worried about magnitudes right now. So this magnitude has got to be equal to this magnitude. Again, similar triangle problem. And we find out that's the sine piece. So what do we have? We notice that we have now established our forces in purely the x and y direction, instead of these kind of angled things. So we know that Newton's second law tells us that the sum of the forces in the system is equal to the total mass of the system times the total acceleration of the system. So F equals ma. But remember, in that equation, F equals ma, F is really this sum of the forces, this sigma thing. So the first thing we want to do here is, normally we could write that total forces as the x forces plus the y forces, f sub x plus f sub y. So let's break them into pieces. This is a good tactic for any kind of physics problem that you encounter. If you ever see something that has x and y components, the sub x and sub y, split them into separate problems. Get all your sub x stuff in one equation, all your sub y stuff in one equation, and come back and add them again later. So in this case, we know the sum of all the forces is all the forces in the x direction and all the forces in the y direction. Well, we have something that looks like an f sub x. We have something that looks like an f sub y. So let's solve for those pieces. The first case we do is we solve for the x forces. So we go sum of the forces in the x direction. Well, let's look at what we have in the x direction. Remember, we said our x direction is kind of along this plane, and we're going to say that our positive direction is kind of down to the left. So our positive x direction, all we have to do is look at the x-axis. Ignore all this stuff in the y, ignore the diagonal now, because we've already accounted for that. Now we just look at the x and y. So we look at our x direction. So in the positive x direction, we have something that looks like weight times the sine of theta. Cool. We have another force along that x direction. That's this F sub lower F, or our force due to friction. Remember, in physics, signs mean direction. If we said that this down and to the left is positive, then up and to the right must by definition be negative. So we add that force, but we have to remember a negative sign when we do that because of direction. So our equation ends up looking like this. The sum of the forces in the x direction is W sine theta minus the force due to friction. All right, next sub-step. We still don't have this in terms of what we want. Remember, we're trying to find the coefficient of friction. We're trying to find this kind of mu thing. So our first objective really should be to work these equations down to the point where they all have a mu in them, because that's what we're trying to find. Well, I can't really do much else with W sine theta. I mean, yeah, certainly I could replace W with mg, but that's about as far as I can break that down. There's not going to be anything that has to do with mu in there. But I do know that mu has something to do with friction. And we have a frictional force. Well, remember, the way we calculate the force due to friction is mu n. So mu is our coefficient of friction. That's what we're trying to find. N is our normal force. So we can say that the sum of the forces in the x direction, all we've done is take this equation, this Fx equal W sine theta minus force due to friction, and we've substituted mu n for the force due to friction, and we get something that looks like some of the F forces, some of the X forces is W sine theta minus mu n. Notice here in this example that they're using mu sub k. This is something we will talk about a little bit later. There are actually two kinds of friction that we would worry about. There's something called static friction and there's something called kinetic friction. Static friction is the friction between surfaces when the thing is at rest. Kinetic friction is the friction between surfaces when the thing is in motion. They generally are different values. If you want to prove this to yourself, take a box, put it in a mud pit or sandbox, and try to push the box. In order to get the box moving, you're going to require a lot of force. But once it's moving, you don't require as much force to keep it moving. So you have to overcome the static friction first to get it to move. Then apply a consistent force to overcome the kinetic friction as it's moving. Since this problem is about the box moving, we know that we're looking for the static or the kinetic coefficient of friction, and we label that mu sub k. So knowing that, we have our expression for all the forces in the x direction. But remember, Newton's second law tells me that the total, sum of the total forces in the system is total mass times total acceleration. And we said that the sum of the total forces is the F sub x plus the F sub y. We just found our F sub x piece. Now let's find the F sub y piece. This one is actually really easy. We can do this a couple of ways. The easy way is to just apply a little bit of logic and critical thinking. Think about the direction this box is moving. We have the thing sitting on our predefined ramp here. And we've said that the X direction is along the ramp and the Y direction is up and down. So if you think about what's going on with this box is sliding down the hill. There is no motion in what we have chosen to be the Y direction. Right? It's not bouncing up and down as it goes down the ramp. It's not a spring. It's not doing anything crazy like that. So there is no motion in the Y direction. If there is no motion in the Y direction, then there can be no force in the Y direction. So all the forces in the Y direction, our F sub Y, have got to be zero. But if you are not comfortable with that, and you don't want to just make that assumption, you can calculate it. It's the same thing we did before, but instead of the X direction forces, we do the Y direction forces. Well, let's go back to our diagram. And now we're talking about the Y direction. So we have a Y direction force that is W cosine theta. And then we have some normal force. Well, okay, that's all we have. So we can do normal force plus that other Y force. Now remember, we chose our Y direction to be kind of down and to the right. So we have to account for that negative sign. So we get the forces in the Y direction are equal to N minus W cosine theta. Since N is the opposite of W cosine theta, it's got to be a positive. So if you were to substitute N in here, cosine theta, W cosine theta, what you'd get is W cosine theta minus W cosine theta. Doesn't matter what those work out to, those are equal quantities, so they go to zero. It's good for you to show that on an exam, but if you can give me a sufficient explanation as to what's really happening in the system, rather than just write, well, it's zero. If you can give me some verbiage to indicate to me you understand that there is no direction movement in the Y direction, thus there can be no force, then I'm good with that too. So we now know, since that sum is zero, we can solve for N. N equals W cosine theta. Well, look what we have. We already have a solution in the X direction that looks like this. W sine theta, sorry, forces in the X direction are W sine theta minus mu sub K times the normal force. Remember, we're trying to find that mu sub K. If the thing's in equilibrium, then those two forces have to cancel. So we can say, because those forces cancel, the mu n and the W sine theta, the sum of those has to be zero. Since the sum of those is zero, do some algebra, and we find that W sine theta equals mu sub K n. We know what n is, so we plug it in, and we get this. W sine theta equals mu sub K W cosine theta. Well, what are we trying to find? We're trying to find mu sub K. So notice that we have not yet defined W and we have not yet defined cosine theta. Doesn't really matter. These are variables, right? These are actually going to be constants, right? Because the weight's a constant and the angle is constant. So we can treat those two things as constant, do a little bit more algebra, solving for mu sub K. Mu sub K looks like W sine theta over W cosine theta. Something interesting happens here. W and theta are constants, but We cannot just cancel the theta, because then you're just left with sine and cosine, which are meaningless. Those are functions, they don't return anything. So sine theta and cosine theta are two different things. But W is always W. It's the same way. So the W's go away. Let's say that back here up in the step somewhere, or somewhere along the line, you decided to plug in mg for your weight. That's perfectly fine. I will leave that as an exercise for you to go back and work that, putting mg in there. What you're going to find is all the m's and the g's are going to cancel anyway. And you'll find that you can cancel them anywhere along the way. It doesn't matter. As long as you recognize mathematically that they're going to cancel out. The easiest thing to do is to just do it like this. Just leave it as W, work it through. The W's go away. And we find that mu sub k is sine theta over cosine theta. That should look extraordinarily familiar to you. Sine theta over cosine theta, or the sine over the cosine function, is the tangent function of that angle. So that means that the coefficient of static friction is just the tangent of the angle. This is a really profound and interesting solution. Really profound and interesting result. What this tells me, I'm going to show you the value of doing this symbolically. Nowhere in our problem did I give you any numbers. I did not tell you that the box is 100 grams or 1,000 pounds, whatever it is. I didn't tell you theta was 35 degrees or whatever it is. I didn't even tell you we were doing this on Earth. I just said there's some acceleration due to gravity, mg. Well, what if we're not on Earth? Who cares? The acceleration due to gravity is just going to be some constant that's relevant to that planet, moon, Jupiter, or whatever it is. So it's still going to go away. We don't know too much about the surfaces. However, what we just calculated is the coefficient of kinetic friction. If we know that value, we could certainly go look it up in a table and make a pretty good guess as to what these two surfaces are. But by doing this, what we find is the coefficient of kinetic friction. In other words, the amount of effort that you need to put in order to make this box move is only dependent on the angle of the ramp. So play with the equation that tan theta is mu sub k. So you can go play with this in a calculator. Watch what happens when you increase and decrease theta. Look what happens to the value of mu sub k. Ultimately, what you would like to happen is in order to make less effort, right? Let's say we'd want to get mu sub k down to 0. Okay, no friction at all. Well, we could find out where that theta occurs. You'll find that as theta goes towards 90, you're going to get no kinetic friction. And as theta goes towards 0, you're going to get all the kinetic friction. That's all you're going to have. So why is this relevant? Well, let me think of a practical example here. Let's say you're moving. Got a bunch of heavy stuff. and I've rented a U-Haul. And that U-Haul has a ramp. It is easier to take my heavy thing and push it up the ramp than it is to just go stand next to the truck and lift heavy thing straight up and put it back in the truck. So we use the ramp to decrease our workload. In other words, we decrease the force that is required to overcome the force due to friction. And what you'll find is that there's going to be a sweet spot here where this angle is ideal. Now, the smaller you can make that angle, the less force you have to apply over time. But by making the angle smaller, if you can envision this triangle, as theta gets small, the length of this gets long. So if you have something extremely heavy that you want to push up a ramp into the truck, you want to minimize the amount of vertical force you have to do. So you want to turn it into horizontal, but you still got to go up a little bit. And so what you're going to do is find that if you make a really, really long ramp, you can make a really small angle with the ground and your job's going to be easy. Now you're going to be pushing for a while. Ramp's going to get pretty long. Now that's not practical, so we can simply build or engineer our truck and our ramp so that it's practical. So you're going to get something like a 40-degree angle between the ramp and the ground. And then you'll find out that it's easier to push box up the hill. Other things we can do in that example. Instead of just making this a flat surface, we can put rollers there. We used to do this on cargo airplanes all the time. You put rollers, and as we'll see later on in the semester, your rotational friction is generally going to be less than just your lateral friction. So we're going to use those rollers and the properties of physics there to our advantage to decrease the amount of force that we need to roll the box up the hill. Let's see. Yeah. I did find a thing just looking around. Let's see. I think I did a search for inclined plane problem simulations. Yeah, GeoGebra does this really well. So here we can see that if we go into this particular simulation, you can have this all drawn out and you can input these different masses and velocities and whatnot. And this will do all those calculations for you. Now, one thing I didn't talk about yet that this simulation does. Notice we have a T, a V, an A, and a delta X value. That's interesting. It's actually a more interesting problem. It's a more practical problem. What we did in the previous example is we found what that coefficient of friction is. Well, now that I know the coefficient of friction, I know the force. And if I know a force and I know a mass, I know an acceleration. So think back to last section and the thing we just got done with an exam on, when we talk about two-dimensional motion, two-dimensional kinematics. Something is now moving along an angle. This turns into something that looks a whole lot like the cannonball problem, where you have some object of a known mass and it's accelerated for a certain distance, right? Well, if we know the acceleration, because we can calculate that from forces, and we go back to our kinematics equation, we know that the velocity of an object is the initial velocity, v naught, plus the acceleration of the object times the amount of time it has been accelerating. So if we calculated in this example that the acceleration of the object is 5.194 meters per second, at t equals 0, then the velocity is just going to be whatever its initial velocity was. In this case, they've set this thing up to where its initial velocity is -5 meters per second. Remember, direction is negative. In this case, it looks like our positive is going down the hill, so our negative's got to be up the hill, and that's exactly what we drew with our initial velocity. But from that, since we know that kinematics equation, and we can find a velocity. Well, if we know a velocity, and we know a time, and we know an acceleration, then we go to our position function that says our range function that says x equal x naught plus v naught t plus 1/2 at squared. We just calculated v naught. We know a t, well, we could just plug it in. We know an a, and we know our initial x position because we can put that wherever we want. So from that information, what we can find is our range, our delta x. So you see how all this kind of comes together. Sometime next week, I'm going to show you guys, maybe not next, maybe the week after that. I'm going to show you guys something called a ballistics pendulum problem. The ballistics pendulum problem is really fun. Imagine you have a weight hanging from a string, and that string is free to move around. So it's, it's like the pendulum on a clock or something. And let's fire a bullet into that block. Well, what's that block going to do? It's going to swing. So we'd like to know what the maximum height of that swing on that arc is from the bullet. So that's called a ballistics pendulum problem. One of the things we're going to do here, like I said, in a week or two, is I'm going to show you how to solve the problem. We need a few more tools before we can do that. We need to know something about energy. We need to know something about tension. We need to know something about momentum. So those are places that I'm going to go here over the next week or two to give you those tools. And ultimately, we can combine them all into this giant ballistics pendulum problem. And we can do some pretty neat things. Again, notice in all of these problems, we are not worried about air resistance. We are not worried about the angle changing or the mass changing during the period of time that we're looking at. It is possible to do those problems, but not with the information that you're going to have in this class. This is a more advanced level physics problem. You have to have calculus to do it. You cannot do it with algebra, at least not in any way that I would want to. It would take you days. And you have to know something about differential equations to really get a good answer on it. However, we can make some estimates for at least wind resistance. If you wanted to put wind resistance in here, think about wind resistance as just some force. So it's just some force that's acting in opposite to the direction of motion. So it would just be added in just like your kinetic friction. And maybe I'll show you how to do that next time, or show you an example of it next time. It's not really all that hard. The objective and the point is when you're doing these kind of problems, all we're doing is summing forces. That's it. That's all these Newton's law problems are, is look at what forces are there in the X direction and in the Y direction. You probably have to break some vectors apart to do it. But once you have your X forces and your Y forces, add them all up, then add all the X and the Y forces together, set it equal to MA, and there's your solution. This is exactly the kind of problem that I would expect you to be able to solve on an exam. I should be able to give you something that says, given a box of mass M on a ramp of angle theta and some coefficient of friction mu between the two, derive an expression for the range of the box if the box starts at a height h on the ramp. No numbers involved, solve it symbolically, use the equations. And I know that some of you are scared about that. The reason that I do that, the reason I want you to be able to do that is because notice the way I solved this problem today, the way I walked you through this problem today, not using any numbers. It's a whole lot easier to keep track of what's your X direction and what's your Y direction without having to worry about decimal places and factors of 10 and that kind of thing. It is almost, I cannot think of any really strange exceptions off the top of my head where it's easier to do it by putting numbers in first. It is almost always easier to solve any physics problem doing it symbolically, working the equation down to what you need. For example, that mu sub k that we looked for, we worked it down symbolically to where it was just tan theta. No numbers required. And now once I have that, I can easily ask, what's the coefficient of static friction at angle of 10 degrees? What it is at 30 degrees? What it is at 25.69 degrees? Easy to find. We just plug one number into one formula. If you didn't have the symbolic solution and I started asking you those things, you would have to go back and redo the whole thing over and over and over again. But if you solve it symbolically once, then I may ask you 5 or 6 different angles, and it's trivial. That's the point of physics. We want to be able to model and describe our motion in our environment, motion in the environment, all the forces in the environment with very little effort, or at least make it concise and consistent, because I'm a physicist and I'm lazy and I don't want to do all the work. Having said that I'm a physicist and I'm lazy and I don't want to do a whole lot of work, it is Friday. This classroom is all torn up and they're probably going to do some more maintenance in here. And you guys are probably tired of hearing me run my suck all week. So we are done. I will be back on Monday to continue this. As always, if you have problems, if you need help, reach out to me. Or the University Tutoring Center has some of our students, grad students, and some upperclassmen, undergrad, that are over there doing tutoring services for this. So, having said that, I will see you guys next time.